Today we're going to cover our last mini topic in matrices, which is how we solve a certain type of partial differential equation using matrices, and in that way we can sort of combine bits of our knowledge from the ODE section of the module and the matrices section of the module. Okay, I'll hand over to the board now. Okay. So last time we discretized the diffusion equation so k here is a constant, phi is a variable that you're evolving in time, as this. So we had phi m plus 1. So this is actually I'm just going to use the whole line here. This is actually it, although it's a relatively short section in your lectures. It brings together a lot of things. It brings together matrices, brings together your sort of knowledge of numerical discretization. So there's a lot in being able to write this down yourselves without any formal notes. So let's make that I minus 1 over delta x squared, and we made it implicit as well by having the m plus 1s on here. So there's a lot of information in this equation, a lot of assumptions that if you followed every step of the way previous in lecture, it won't be a problem, but there may be little sticking points you want clarification. Come back to me in the live sessions if you want me to go over any of these other aspects again. So we're going to rearrange m plus 1 terms on left hand side, n terms right. By the way, there's a reason we've made this implicit. It's for numerical stability. If we didn't make this implicit, if we put this at step n, it wouldn't work actually. For it to be numerically stable, we need to make it implicit. So the implicitness is important. So implicitness improves numerical stability, and more on that later in the module. By making it n plus 1 rather than n, it's important. But the consequence of that is that you can't step it forward in an explicit way without matrices. You have to rearrange it and make a matrix equation. So what we're going to do is define how I'm going to do this. Let's do it. All the steps, shall we? So if we multiply through by delta t in that previous equation, we end up with phi I n plus 1 minus phi I at n equals k delta t delta x squared, taking out these factors, phi I plus 1 minus 2 phi I plus phi I minus 1, and then we'll do it all at n plus 1 here. Okay, all these are typeset really nicely in the lecture notes. So I'm almost running out of space at the right hand side here, but you can see clearly what's going on. The reason I've done that is delta t, delta x, and k are constants for this problem. So it's helpful for further analysis to take out this constant, not take it out, but just bundle it together into a single constant. So I'm going to define a nu as k delta t on delta x squared. Okay, and that just makes the algebra, sorry, there should be brackets around this as well. Okay, it's going to make the algebra a little bit easier. So that will give phi I n plus 1 minus phi I n equals nu, just expanding out those brackets. Let's move that back a bit. Oh, stop. Minus 2 nu phi I plus nu phi I minus 1 and plus 1. So that's really helpful. Nu just makes the algebra a little bit easier, and we can see that we can bundle together n plus 1 terms and n terms. We can bring the n terms onto the right hand side. There's just phi I, the n there, and then we can bring all the phi I, the n plus 1 terms over the left hand side. Okay, so that implies that so minus mu phi I n plus 1, it's 1n plus 1 terms, then plus 1 plus 2 nu phi I n plus 1 minus nu phi I plus 1 n plus 1. That's the left hand side. By the way, I'll put it down here. Nu is, I'll do it in LaTeX, is nu. Okay, that's why I'm probably, okay. It's a Greek letter, and I'm pronouncing it nu. That should be I minus 1 there. Okay, so we brought all the n plus 1 terms in the superscript over to one side. These nu's are all constants for a given problem. And we've got the terms in I minus 1 here, terms in I here, terms of I plus 1 equals that. So that's our left hand side, and then that equals, so there's not enough room to put it on one line, phi I to the n. So this now looks in a similar form. So the left hand side is now in a similar, although there's more indices, form to the boundary value problem. It's no surprise because we're applying a second derivative in space, which is exactly what we did in the boundary value problem. The only complication here is that we've also got the time derivative, but it's a similar thing. Whereas you have an I minus 1 term with a coefficient, you have an I term with a coefficient, an I plus 1 with a coefficient, and then a right hand side. And we can then turn this into a vector problem. So we're going to put all the entries, if you like, of phi I n into a vector y n. You see what I've done? So all the I values, all the values in x, depending on how many you have, we haven't specified, but they all go into a vector y. So y vector n contains the spatial distribution of phi at any one point. Okay. And then so our our equation can then be put in the form Ty of n plus 1 equals y of n, where T is a matrix. So what I'm going to do now is show you what this matrix equation looks like, and it's related. So basically each step, so at each time step, we invert a matrix T to find a new step. And this is the trade-off, if you like, of using implicit methods. Implicitness improves the stability of the problem, but it has an extra computational cost of doing this matrix inversion. Let me now show you what the matrix looks like. So this is going to take the whole board, I think. We have a matrix here, and a vector. Let's try again. Here we go. Again, it's all neatly laid out, but it's good for someone to go through it, I guess, in a paced way in the lectures, even if the written presentation is not quite as neat as the lecture notes. So this is going to be our matrix T. This is going to be our vector. This is going to be our vector y n plus 1, and this is going to be our vector y of n. And remember, the vector y contains all the elements of phi. So phi I n plus 1 phi I minus 1. So some people might prefer to not define a vector y and just go straight to the matrix form from the original equation. It's kind of up to you really, but so remember we had an equation with three components at n plus 1, depending on I minus 1, I and I plus 1, and then on the right hand side we simply had phi I of n. So now we need to just define the coefficients that go in there. So this is the diagonal element of the matrix. So this is diagonal. By the way, we're not going to deal with the boundary conditions in this case today. I'm just going to show you that it resolves into matrix problem. And then we've got minus mu in the off diagonal, minus mu in the top diagonal. Yeah, these spread out. And so those coefficients then copy all the way up the matrix, and then further down as well. Okay, and then everywhere else is zeros often. So this is a very common way with numerical methods. You quite often have matrices that are quite sparse. By sparse I mean there's lots of zeros. And so that sort of space around is zeros, and we don't just fill it in, we're just interested in the central thing. But the thing to think about is that we've got, via matrix multiplication, we have these coefficients minus mu, 1 plus mu. Let's try again with that. That's minus mu there. Minus mu, 1 plus mu, minus mu. There are three elements there, and they multiply through by these three elements here, and then they equal that element. Okay. So quite a lot here. I realise that this is an integrated little bit of topic at the end. We're integrating our differential equations with some stuff on our matrices. But this is where we can go. This is quite more advanced from where you were last year, I'm sure, that you've got an implicit solution to a partial differential equation. So we're really moving on with our sort of knowledge. So what I commend you to do is look at that matrix and see if you can convince yourself that multiplying these three elements by these three elements gives you the right hand side, and that corresponds to the discretization, which is 3 lines above in the lecture notes. So this in lecture notes is page 55 of lecture notes. There's about 100 pages of the lecture notes which carry on, you know, through to middle of term 2. So we're trickling on with the information now. Okay, so maybe if I can just write it down here, what this expansion is in time. So it was minus mu times phi I of n plus 1. That was that element there, multiplied by that element there. Sorry, phi I minus 1 n plus 1. Then plus 1 plus 2 mu phi I n plus 1. There's that one there. And then minus nu phi I plus 1. Minus nu phi I plus 1 n plus 1. Okay, then that equals phi I n, which of course is this final term. And then of course this equation applies for all I, so basically that's why we have it as a matrix, so we repeat the coefficients all the way up and down the matrix. Okay, at least you can see how it works. Okay, so I'm going to stop there. And next time we will start a new topic, which is optimization. That's the last topic of term. You can breathe a sigh of relief. And I will see you then. Bye for now.